So now that we have devised a code generation strategy and discussed the implementation of all possible constructs or constructors in our language, let's look at a real example, a concrete example, and look at how we are going to generate code for that and what the generated code is going to look like. So let's say my program is the following. It's function definition. There's only one definition, one function, sum2 x, which is defined as follows: if x equals 0, then 0, else x plus sum2 x minus 1. So this is a recursive function that computes the sum of the first x integers. Right? So this is a valid program in our language, and we want to generate code for it. So how are we going to generate the code for it? Recall that code generation is a top-down procedure. So we are going to call cgen on the top level construct, which is the function definition itself. And then we are going to look at the rule for that function definition. So the first thing, recall what is the code that's generated for a function definition is basically we generate a label for that function, sum2 underscore entry, and then we do some basic stuff so that we set up the AR properly. For example, we load the frame pointer, we reinitialize the frame pointer, we save the return address, which is in $array, and that's it. And then we can generate the code for the expression of this function, which is on the right side. Okay, so let's see. All right, so that's exactly what we're going to do. Firstly, we're going to do a label for sum2 function. Then we say move $sp to $fp. So we initialize the frame pointer, and then we push the return address on the stack using these two instructions, store word and add IU. The next step is to generate the code for the body. So we're going to call cgen on the body. And what is the body? Body is an if then else construct. So we're going to look up the if then else rule. What does the if then else rule do? It basically first computes the first left hand side of the equality, which is x. Then it computes the right hand side of the equality, which is 0. Then it checks whether they're equal, and depending on that, it either jumps to the true branch or the false branch. Also, after it computes x and before it computes 0, it pushes to the stack, and before it branches, it pops from the stack. These are all rules that we had discussed from the code generation implementation of if then else. All right, so let's go start with that. So the first thing we're going to do for the if then else is to compute the left side of the equality relation x. So for that, we're going to call cgen of x. And recall cgen of x is going to, which rule is it going to use? It's going to use a rule for a variable reference. And the variable reference in our code generation strategy is going to come from $A0, load word $A0 from address 4 plus fp, because x is the first argument. So it's just 4 into 1 plus $fp. So that's 4 plus fp, and that gives me x. And now I want to save that on the stack. So I'm going to push that on the stack because of my if then else code generation rule. So I push store word $A0 on sp, that, and then decrement sp using add IU. So I push A0 on stack, and then I generate the code for 0. What's the generated code for 0? Because we haven't probably discussed this. We discussed this right in the beginning when we said that what is the code generated for a constant, and so 0 is a constant. So cgen of a constant is just load word that constant into $A0. So that's the code for 0. All right, now we have to move on with the rest of the code for the if then else construct. So what is the rest of the code? We are going to first pop the extra space that we have created for storing x here. And then we are going to do the branch equals instruction to either jump to the true branch or the false branch. So here's the code for that. So I omit some of the initial code for setting up the activation record. The code for loading x, pushing x, loading 0. Then I'm going to compare x and 0. So for that I load 0. I load x into T1. I pop off the stack because I had pushed into the stack, so I pop off the stack. Recall this is because of our invariant that the stack should remain unchanged. And then I branch either to T, I use branch equal to on T1 and A0 to to either jump to true 1 or false through to false 1. Okay, so this is just, we're just pattern matching on the if then else construct and just substituting cgen e1 for the code for generating x and cgen e2 for the code for generating 0. Alright, now let's look at the individual labels. What should happen on false 1? So false 1 is basically when I am here in the else branch, right? Because that's what the false, the condition is evaluating to false, and that's where we will go. And so at the false branch, I'm going to do code gen of this particular expression, x plus sum 2 x minus 1. And so for this code gen, I'm going to use the plus, the rule for the plus. And the rule for the plus is that first you generate code for the LHS of the plus, the first operand, then you generate code for the second operand of plus, and then you add them, right? So that's what I'm going to do. The first operand of plus is x. So what's the code generated for x? That's just load word $A0 $4 FP. We have seen this before. Then I'm going to generate the code for sum 2 x minus 1. Now this one is going to match with the rule for function dispatch. And so I'm going to call cgen on the function dispatch, and with the function identifier as sum 2. And so I'm going to jump to sum 2 entry because of this, and jump and link. And then before I do that, I need to compute the arguments, and I also need to set up the activation record. Alright, so we're going to first set up the activation record. So before we do that, in the rule for plus itself, I need to push the value computed for the first operand. And so I first push the value of x. And now I start setting up the activation record. The first thing I do is I push the current value of fp on the stack. So that's going to form my old fp. So this is what my newly constructed activation record starts looking like. And then I compute the argument x minus 1. So to compute x minus 1, I first compute x, because I'm going to use the rule for subtraction. We call cgen x minus 1. So I first compute the first operand, which is x. Then I'm going to save the first operand on stack, then compute the second argument, and then do the minus. So for the first argument, I just do load word A0 $4 FP for x. We've seen this before. And then I push x on the stack. Recall that I'm using the rule for minus. And on this slide, I have more space. So I'm going to now that I have pushed, so here, this is where we were last time. This is where we were on the last slide. We had just computed x, and then we have pushed x on the stack. Now we compute the second argument, which is 1, which is just load immediate $A0 1. And then I basically want to do the subtraction, and for that I use a temporary register. I load x into the temporary register, and then I use the subtract instruction, which does t1 minus a0 into a0. At this point, at this particular point, just after the subtract instruction, the value is in a0. The only problem is that I had pushed some stuff on the stack because of the first operand of minus. And so going by the rule for minus, I'm going to pop off the stack, pop up one word of the stack using the addiu sp4 instruction. All right. Also, I'm done. I'm not done yet. I need to also do the plus, right? So this was just, I also need to call the function. Right now, I've just prepared the argument, which is x minus 1. Now I actually need to call the function. So let's see what's the next thing. The next thing is I store the computed value a0 on the stack. So this is the first argument. Recall that arguments live on stack. Then I addiu sp minus 4. So I just pushed it on the stack, so we can also decrement. And I'm almost done. I just call your sum 2 entry using the jal instruction, jump and link instruction. And that's my function called dispatch. After the function called dispatch, I also need to do the addition, right? So I haven't shown that yet. So here is the code for addition. So just after the jal, when it returns at this particular point, I can assume that the return value of this function is available in a0. And so now what I want to do is I want to add x to a0. But where is x? All right. So x was, because of the plus operator, I had saved the value of x on the stack, and I'm assuming that because of the function call, the stack hasn't been changed. That's the invariant we are maintaining. And so I can assume that stack x is at the top of the stack, and where's the top? That's just 4 plus sp. So I load x from 4 plus sp to t1, and then I execute add on t1 plus a0 to store in a0, and that computes x plus retval in a0. Finally, because of the plus operator, I had pushed some x to stack, so I just pop off that stuff from stack. At this particular location, I have computed the value x plus sum to x minus 1 in a0, and I have cleaned up the stack to exactly the state where it was before I started this computation. And so I'm done with the entire body of the else part, and I can branch to end if 1. Notice that I'm using this suffix called 1. This is just to basically disambiguate between different if then else's, right? So maybe there are nested if then else's, or different functions are different if then else's, and so on. And so you can just give them numbers depending on which one it is, and based on that you can disambiguate between different labels. Similarly, let's look at the code for true one. That's actually much easier. On the true branch, it's just 0. So I just do load immediate 0 into a0 and branch to end if 1. Okay. Notice that this code is also satisfying our invariance. It's loading the value into a0 and leaving the stack unmodified. Finally, end if 1. What is end if 1 supposed to do? It is supposed, now I have computed the expression. Now the instructions that are supposed to execute after this are the ones that are due to the function definition, the function declaration. And so recall that what is the function declaration, what is the footer of the function declaration code? It is load word from the top of the stack into $array. So get the return address into $array. Pop the stack by z amount, where z is equal to 4 into n plus 8. Recall that's just coming from our rule, and here n is just 1, the number of arguments is just 1. So 4 into 1 plus 8 is 12, so I add 12 to sp. I load the old 4 frame pointer into $fp, once again coming from the declaration rule, and then I call jar $array to return back to the caller. And that is indeed the full code or implementation of this function sum to x.